Hey guys, welcome back. So what we're going to cover today is minimum spanning trees and what to look out for and how to determine whether or not you actually have a spanning tree. So let's just start off. What is a tree? Now you can think of a tree as just like a basic family tree, as you can see on the screen here. And that just shows the connections between different people and also their children and also the relationship between them. So for example, you obviously, if this is you have your brother, and on above you, you'll have your parents, and on this other side here, you're going to have the relatives of your parents. In this case, your aunt and your uncle, and likewise your cousin. So the connections between them, or the edges, just represent kind of the relationship between each individual. And you'll see above here there's a technical definition. So a tree is a network in which any two vertices are connected by exactly one path. Okay, so as long as you have two dots and there's one connection between them, you've got yourself a tree. So if I add another dot here, make another connection, that's a tree. Now in the second part of this sentence, it says this means that this means that a tree is connected and has no cycles. So that's very important. A tree has no cycles. So if I were to create another tree here like this, and I would make another connection here, this is not going to be a tree because you have this extra connection there, which makes a cycle. Now we'll talk a bit more in a second about what will determine whether or not something is a tree, but for now, just recognize that there has to be exactly one edge connecting two vertices, and also you cannot have any cycles. All right, so let's have a look at these examples. For each network, state whether or not it is a tree. Okay, so if you look at all these, let's just go through these one by one. This network here has 3, 4, 5, 6, 7 vertices, and they all have one edge connected to them. So that satisfies that previous criteria. But also one more thing I haven't mentioned yet is for a tree to exist, a tree must be connected. So that just means every single vertex needs to be connected. So this is a tree, yep. Now you can see here for B, you've got part of the network here and a part of a network here, which is actually not connected. So this is not a tree. Now C, you can clearly see, for those people with a keen eye, there's a loop here, or a cycle, so this won't be a tree. D, looks like all your vertices are connected, so this will be a tree. And then lastly, E, you can see here that there is an unconnected vertice, or another word for vertice is node, so that won't be a tree. Okay, pretty straightforward definition of a tree. Okay, so let's have a look at what a spanning tree is. So a spanning tree is a type of tree where every vertice is already connected, and you're actually drawing a spanning tree off a regular network diagram. Okay, so below here is an example of a network, A, B, C, D, and there are multiple connections. So straight away we can tell that this is definitely not a tree, it's just a network. Now it's not a tree because there are cycles within this network, but what we can do is we can actually draw a spanning tree from this network. And all that means is we're going to draw each vertice together in a diagram and make sure that they're all connected and it creates no cycles. So have a look at these 4 examples here. These are 4 examples of possible spanning trees that you could draw from this one alone. So here A, D, B, and C are all connected. Likewise in these configurations as well. Now this one, just beware, there's no vertice here, so you're actually okay. There's no cycle here, okay? There is no cycle here, so this is actually okay. Now one more thing to note here, if you have a look at how many vertices there are, let me just write down here. For vertices equals 4, and what are the edges equal to? 1, 2, 3 edges. Okay, what about this one? Vertices equals 4, and edges equals 3. So there's a bit of pattern here, isn't there? Vertices equal 4, edges equals 3, vertices equal 4, edges here is, count them, 1, 2, 3. Okay, now that's no coincidence. So for a spanning tree to exist, we'll have, if it has n vertices, the edges will always be 1 less than the number of vertices. So that is an important thing to remember. It's not difficult. It's actually quite obvious if you think about it. There's always 1 less edges than there are vertices for spanning trees. Okay, let's have a look at this example here. So determine whether each graph is a spanning tree of the network shown on the right. So here's our network, and we want to see if these 4 will be spanning trees. So A, let's look at the first one. Ask yourself, are there any cycles? No. And are all the vertices connected? Okay, so I've got A, B, C, D, E, F in my original diagram, and here I've got A, B, C is connected, D is connected, E and F is also connected. So this is yes. Now B, straight away I can see I've got myself a cycle here, so no, this won't be a spanning tree. Okay, C, is it a spanning tree? So I don't see any cycles, and it looks like all my vertices are also connected. So that is a yes. And then lastly, you can see clearly that D is not connected, so this won't be a spanning tree. All right. Okay, so there's just one more idea to cover before the end of this video, and that's the idea of a minimum spanning tree. So what's a minimum spanning tree? So here I've just got a simple example. So imagine you have a set of cities and you want to build roads between them in the most cost-effective way. A minimum spanning tree would be the set of roads that connects all the cities without any loops, remember, such that you've got the lowest cost. So the only thing we're building onto what we just learned about spanning trees is we're finding the edges which will be the smallest in value to create our minimum spanning tree. So let's have a look at this example. This network represents 8 computers that are to be connected with optical fiber cable. The numbers show the cost in $100s of cables. Draw 2 spanning trees for the network and determine which is the cheaper option. Okay, so it's pretty straightforward. Let's have a look here. So I've just got to draw a spanning tree connecting all the vertices, making sure there's no loops. So I'm kind of just connecting as I go, and let's see what we get. So I've connected those ones. Now I'm going to go from C to D, D to F, D to E. So if I just redraw that, A, B, H, G, C, D, F, E. Okay, so just labeling this, I'll have 4, 2, 3, 5, 3, 2, 4. So all my vertices are connected and I don't have any loops or cycles. So the weight of this is going to be 4 plus 2 plus 3 plus 5 plus 3 plus 2 plus 4. 4 plus 2 is 6. 6 plus 3 is 9. 9 plus 5 is 14. 14 plus 3 is 17. 17 plus 2, 19. 19 plus 4 is 25. But because we're in hundreds of dollars, this will be times 100. That's $2,500. Right, cool. They want us to draw one more, so just get rid of this and draw another one. Okay, so instead of going up, I'll go down this time. So A to B, A to C, C to G, G to H, D, C to D, D to F, and F to E. So I'll just draw my second one here so you can see. Move this down a bit more. All right, there is my second spanning tree. Now I'll just add up all the weights. So 4 plus 6 plus 5 plus 3 plus 3 plus 2 plus 4. All right, 4 plus 6 is 10. 10 plus 5 is 15. 18. 21. 23. 23 plus 4 is 27. Times 100. So this is 2700. So this will be my cheaper option. Okay, so that is what a minimum spanning tree is. Now, for those of you who are probably wondering, it would take forever. Well, not forever, but it'll take a long time to actually trial and error in order to find out what would be the minimum spanning tree. So in the next video, I'm actually going to go through a process, or another technical word is an algorithm. It's basically just a recipe that you follow in order to get the minimum spanning tree every single time. And it's super, super handy. But I'll go through that in detail in the next video. Once again, if you have any questions, let me know in the comments. The notes will be in the description. And hope you enjoyed. I'll see you in the next one. Peace.